Hi, I want to talk today about IPv4. Later we'll be talking about IPv6. If you haven't watched the conversion video from dotted decimal or decimal to octal, decimal to binary, decimal to hex, I'd watch that now. This is essentially the second part and IPv6 will be the third part. Today we're going to be talking about two different concepts associated with IPv4, and the first one's going to be classful. So during classful routing, you have different classes that are associated with it, all the way from A to E. It goes based on size. So A is the largest, E is the smallest. And in this scenario, you have A is for large corporations, and you just have to essentially memorize these numbers, and then I'll go into what it means for dotted decimal per octet. So IPv4 takes 32 different bits and IPv6 takes 128 different bits, and each section is an octet because they have 8 different bits associated with that. If you convert 255 to its octet binary representation, then essentially you have all ones, and so that's why they refer to them as octets. Going further, with classful routing, you will have IP addresses that fall from 0 to 127, and the first octet being, they belong to Class A. For Class B, it's going to be 128 to 191. Class C is 192 to 223. Class D is for multicast applications and protocols, and that's going to be 224 to 239. Class E was originally developed for experimental IP addresses, but today we've run out of IPv4 addresses. They're very expensive. You can't go online and buy a single IP address. You have to buy a block, and it'll cost you $5,000–6,000 just for a 24 subnet block. So what have we done in the industry to combat that? Originally, we worked with NAT, static NAT, which is network address translation. Then we looked at double NAT, and we looked at port address translation. And so when you're talking about private IP addresses, and what the industry uses behind their NAT, essentially, is going to be 10 to its broadcast domain or broadcast address, which is 10.255.255.255. For smaller private IP addresses and networks, you're going to do 172.16 all the way to its broadcast address, 172.31.255.255. And the smallest one is going to be 192.168 all the way to its broadcast address. And so that's going to be IPv4 addresses, and this is specifically for classful. And we'll go into the conversions and the mathematics behind it. Let me erase this and show you what classless interdomain routing is, or CIDR. And essentially that's very important when you're looking at firewall rule sets, when you're looking at creating routing prefix lists or distribute lists or route maps. Essentially, you're using those prefixes to be able to match whatever IP addresses you're looking at within that range with higher fidelity. And so let's talk about let me erase this really quick so there's no confusion. So that was classful routing for IPv4. Now we're talking about CIDR, which is essentially going to be classless interdomain routing. And this is when you're talking about subnet masks that are not standard, like 8, 16, 24, 32 even. So these are going to be the subnet masks that are in between that. And let's do an example. So let's do 16 192.23.14.2/12. So the subnet mask is going to be 12, and that falls in between a class A and a class B. So what that means is, if you're looking at this strictly from classful routing, then essentially this would be a class A, because it falls between 0 and 128. However, in this scenario, when you're working with route maps or you're working with firewall rule sets, you want to have the CEIDR associated with it so that you can give a better fidelity and have more granularity in the control. So if we were to convert this to bits, which we will do in a second, we can then determine the network ID mask associated with it and the broadcast ID. And that's very pertinent for different types of IT certifications like Cisco or CEH when you're working with Nmap. Essentially, when you break down the subnet mask into bits so that you can determine the host ID and the broadcast ID, then you can start narrowing down what your actual targets are, or if you're on the defense side, you know, what your assets are that you need to protect. So let's get rid of this line so it doesn't cause any confusion. Let's get rid of the whole thing, make it easier. So in this case, once again, if you haven't watched the other conversion video, you should. But let's convert each of the different octets. So the easiest way to do this is to make 8 underscores for each section, and then count how many bits are associated with that by looking at the largest number that would go into the number of interests that you're looking at without actually going above it. So let's look at the first octet, and in this case we're looking at 16, and for binary, 16 is actually going to fall perfectly along one of these slots where it's only touching one slot. So in this scenario, this would be a 0 or a 1, then you have 2, 4, 8, 16, 32, 68, and 128. When we're working with IPv6, it's going to be larger, and so they switch to hexadecimal. Here we're just working with dotted decimal to binary. So if we were to do this, so once again, 0, 1, 2, 4, 8, 16. And 16 minus 16 is going to go in equally. Let's go to the next octet. So we're looking at 23 in this scenario. Once again, you create 8. And let's go through 0, 1, 2, 4, 8, 16. So we have 16. This is help. I apologize. This helped me on my Cisco test, where I'd write down underneath how much I have so far so that I can keep adding it to eventually subtract it so that it's 0. So below that, you write 16. And so now we're looking at what could possibly add to 16 that may equal 23 or be a little less than 23. So in this scenario, if we added 8, which is the next slot within our binary conversion, we would actually go to 24, and that'd be too much. So we go 1 over to 4. So we make that a 0. We go 1 over to 4, and you add 4 to 16, and now you get 20. And that's still not enough. So we go 1 more over, and that's 2. 2 to 20 is going to be 22. And then I don't need to write down adding 1. But essentially, that would be that octet's binary conversion. And so we're going to look at 14, or the third octet in this scenario. So 14 is going to be less than 16, and so a shortcut is going to be determining the middle and whether it falls to the right or to the left of the middle. So in this scenario, and in all scenarios, this is 0, 1, this is 2, this is 4, this is 8, and that's 16. So if you can remember that on the left it's 16 and on the right it's 8, that'll help you narrow down and help you convert to binary faster on your Cisco tests and on your certified ethical hacker tests. Be able to do this within 10 or 15 seconds is probably ideal. If you can get it to 30, down to 30 for your test, that's ideal as well. So you're given a problem set where you're given a whole paragraph, and 2 of the sections within that paragraph require you to convert to binary to then determine the subnet host. I'm sorry, that last video got cut off a little bit, so I'm going to start talking about the middle of each octet. If you can remember that the right side of the middle is 8 and the left side is 16, that'll narrow down and it'll help you get quicker on determining the dotted decimal to the binary conversion rate and what the number is supposed to be for each octet. This is important when you're talking about Cisco or when you're talking about certified ethical hacker, because you're required to know within 30 seconds or less what the subnet host or what the broadcast address is for that particular network. So when I'm talking about subnet masks, that's very important when you're looking at different route maps, because depending on what the prefix is or depending on what the policy is, you actually may be filtering that route, or you may be allowing it to go to the next step within the route map logic chain. So in this scenario, we're looking at 14. If you go to the left, that's going to be 16. That's going to be a little too much. So we already know that 8 is going to be in there. So once again, you want to add them. So you have 8. So if you go to the next one, which is 4, that's still going to be less than 14. So you can add 4. Now, we're looking at 14, and so far we have 12. And if we add 2, that's going to be perfect. That gives you 14, and that's the binary conversion for that octet. Now the next one's very simple, and it's very simple because it is 2. So remember, 2 is the second slot, and those are just positions that you'll have to remember, and it took me a while to get used to it, and it shouldn't be too much work, but once you get acquainted with it, it's hard to forget. So in this scenario, you have 6 leading zeros, 6, 1, and then another 0. And so what I'm really concerned with here is talking about the network ID, the broadcast ID, the classless interdomain routing, which we covered, talking about how to determine where the differentiator is for the subnet mask. So in this scenario, let's focus on this slot right here. And so this is determining the subnet mask position. And so you have 12 to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And everything to the right is subject to change. So in this scenario, let's rewrite it. where you have 16, 23. Let's start over. Where you have 16, and then you determine how many are left over here on the left side of your subnet mask for that particular octet. In this scenario, 0, 1, 2, 4, 8, 16. So you automatically have 16. But the problem is you can't just take 16 and put it over here and say, that's a subnet mask for the rest of it. What you have to do is then you have to clear the rest of the zeros. And then all ones point, we're able to determine the subnet mask, and we're able to determine the broadcast address. Because from here on out, you just put all zeros for the subnet mask and you put all ones for the broadcast address. And I'll let you do the math in this scenario associated with that. It's not very complicated. So in this scenario, you add 8 for the broadcast address, you add 4, you add 2, you add 1, so that's 3, 7, 15, plus 16, which is 31. And so originally, when we're talking about our subnet mask, broadcast address. And that's really the breakdown for determining classful and classless interdomain routing, dotted decimal to binary conversions. We'll cover more of this later on, especially when we're talking about prefix lists, distribute lists, route maps, different firewall rule sets. I just wanted to get you guys acquainted on what broadcast addresses are, what subnet masks are, and essentially how to determine how many subnet hosts you have on there. And that last one's important, but we'll cover that more later on. So thank you for watching, and I can't wait to see you on my video later on.